cloud server.
Recording on multiple platforms. We're good to go, I think.
Okay, share the screen.
Sure.
Yes.
Or we can start with, well, I was just going to say we're continuing with the third lecture in a series of lectures by Andrea Montanari on mean field methods in high dimensional statistics and non-convex optimization. There will be another exercise session. This lecture will be recorded, so in case you don't want to be recorded, you should turn off your video and your microphone. The lecture will it will be followed by some questions that will be in a non-recorded portion. You're also welcome to ask questions over chat. And after the lecture, there will be some breakout rooms, and then 30 minutes later, there will be an exercise session, again, led by Michael Santano. And then tomorrow, we will be following with the fourth lecture in this series of lectures. So let's share the screen now.
Okay, so okay, welcome. Thanks for coming. I hope I didn't confuse everybody during the last lecture. So I'll start by giving a summary of what we did in the last lecture. We looked at this generalized regression problem in which we have data that are xi, yi, and xi are vectors. So in our model, the xi is for normal zero identity, and yi are responses, are real variable that are, you know, a function, nonlinear function applied to θ0.xi, and the wi are noise variable. And my objective is, given the data x and y, reconstruct θ0. And then I described the standard kind of statistics approach to this, or one standard statistics approach that is minimize a cost function that typically has this structure as a sum of a data points of a loss applied to the data points plus a regularizer. And then I described a general class of first order methods that you can think of either as you know, algorithm to optimize cost functions of this form, or more generally algorithm to process the data. And these are any sorts of algorithm that basically proceed by multiplying by x and x transpose. So these are really characterized by the way you query the matrix x. You query it by, you know, storing some vectors and multiplying by x and x transpose. And, you know, gradient descent and many other algorithms, accelerated gradient, proximal gradient, fit to this framework. And so the question is, can we come up with a general theory of how these algorithms perform, and what is the optimal choice? And of course, we are so far from having a general theory, but I described the theorem, and the theorem assumes that these data are normal, as in my example here. So the matrix X is the matrix with ith row equal to xi's. I stated this theorem assume that the xi, this Gaussian model for the data. Then for any GFOM, what we get is that, you know, the limit of the estimation error, which is what we are interested in, is lower bounded by the limit of the estimation error of a certain specific GFOM that is base AMP, and this itself can be computed explicitly through something recursive, you know, a set of equations that is called state evolution. Okay, and I described a little bit these two algorithms, you know, two type of algorithms of this type in a special example that is sparse regression. But I didn't, you know, prove the theorem. And I will not prove the theorem because I will not have time to do it, but I will try to convey, you know, the basic ideas of this theorem and the proof of this theorem today. Along the way, I introduce a bunch of other interesting concepts, hopefully interesting. But okay, so I decided that actually for explaining the basic idea is better to use a simpler model. And the simpler model that I will use here is the rank 1 matrix estimation. And this is related, I think Leo has given a talk, Leo Miolanor will give a talk in this school. So he will talk about this type of problems. And I think Jean-Christophe Murat also talked about this type of problems. Now, the reason why I don't like particularly this type of problems is that they're not particularly interesting from an applied viewpoint. They're not as interesting as regression, but definitely the math is, simplifies. I mean, in the sense that, okay, we'll see in what sense. So this is a model in which the unknown vector θ0 is again a vector with IID entries. You have a noise matrix, which is a GOE matrix. And what I mean by this is a symmetric matrix with entries above the diagonal that are normal 0 or 1 over n. And on the diagonal, okay, the convention is taken 2 over n. And then you don't observe θ0, but you observe θ0 transpose plus noise. And here the scaling 1 over n is such, is chosen so that the two pieces in this, here and here, the signal and the noise have the same operator norm. Okay, so they are comparable. Okay, so this is the problem. You are given an instance, a realization of this matrix, and then you want to estimate θ0. And this is, of course, it's closely related to things like community detection. Of course, or inferencing graph. It's a simpler model, but it's related to those. Okay, so what would be here the classical, M estimation approach, optimization approach to such an estimation problem would be, one example would be, okay, you try to minimize some loss function of the form, let's say, x minus 1 over n, θ transpose, plus perhaps some regularizer of θ, okay? So this is Frobenius norm. This is the log likelihood. So this is minus log p θ of x. Okay, and this is a regularizer to enforce the desired structure, the desired empirical distribution, perhaps. What would be a GFUM in this context? An example of a GFUM would be, or a way to define GFUM would be to say, okay, what I'll do is that I look at all algorithms that operate by multiplying the previous estimate by x. So you compute some function and I remind you that here the convention is that f1 is a function that is from RT to R, and I apply it, row-wise to the n by t matrix formed by θ1, θt, and perhaps you add some other function. Okay, so basically this includes, you can write in this form any sort of algorithm that you can think of as I do entry-wise operation on the previous vectors, and then I multiply by x or I multiply by x transpose. And if you write down the gradient descent with respect to the objective Ln, this objective, you can check that actually takes this form. And actually it's quite difficult to take algorithm, to think of algorithms that don't do this. Well, of course, there are examples. For instance, if you take the matrix X and you do some operation entry-wise to the matrix X, that doesn't fit this structure. Now, what are AMP algorithms? Approximate message passing algorithms are a special subset of this that do basically the same. So I'll call the function lowercase f just to be clear that is another set, is not necessarily the same set of function. And then the key thing is that here the term that you're subtracting is special. So that's -1, and then there is θ1. Okay, and here these coefficient b's are computed by taking the derivative with respect to θi. Okay. Okay, so this is the algorithm. You do the same thing, that is compute an operation entry-wise on the previous vectors. So here, of course, my convention is that and the idea is that this is just the vector with entries, ft of θ, 1i θ, sorry, ti. Okay.
Andrea, I think it should be the partial derivative with respect to theta s, right? Or
right. Sorry. Good point. Luckily. Okay, now messed it up. Otherwise, would not depend on s, of course. Right. Did I make any other mistakes? Okay, so fine. I will not.
I think you lost the t2 when you erased, but yeah.
Oh yeah, sure. Okay. Okay, now perhaps it's approximately correct.
Sure.
So I will try to describe later at the end of the lecture why where this special structure come from. The special structure of the subtract of the term that I'm subtracting, but it should be clear at this point that this is a special case of GFUM. Okay. Now there is a special case of MP algorithm is what I call the base MP. Okay, let me define that as well. In that case, I take a special form of this function This is just the expectation of the random variable theta given xi t theta plus square root of xi t z equal xt. Okay, and the xi t is computed recursively as where here expectation is with respect to theta with distribution p theta and z with distribution Gaussian independent. Okay, so and then I once I iterate this, the base MP algorithm estimate any vertex as just the function. Okay, so there are two quantities in the algorithm. One are the theta, and the other the theta hat that are the function of the theta. Okay, now I introduced all of these things. So this is a very general class of algorithm that includes, gradient descent, proximal gradient, etc. This is a special subclass. The AMP is a special subclass that so this is a very general class. The AMP is a special subclass in which this memory term, this subtracted term, has a special structure, and then there is a special AMP algorithm that depends as a special form of the nonlinearity. Okay, and now the theorem that I stated before, in this case at least, a consequence of this theorem is that basically for any such GFUM, here, a metric that you can use is the angle between the two vectors, theta naught and theta 0. So this is the cosine of the angle. You want it as big as possible. And this is what? This is the bump. And this is, if I didn't make calculation wrong, is square root of psi t. Okay, so now let me comment on why I chose this rank 1 estimation problem instead of the regression problem to explain things, is because all of these equations become simpler, right? And in particular, if you look above, instead of multiplying by x and x transpose and having two sets of vectors u and v, I have only one set of vector theta. Okay, so the theorem says that bump is the optimal GFUM, and I can predict its value. Okay, so this proceeds in this step, the proof. The first step is a reduction. And by a reduction, what we mean is the following, that, okay, the lemma is for any GFUM, and here there are some technical assumptions about continuity of the update function that I will not state, but let's say that it produces a sequence of iterate theta bar t. There exists an AMP algorithm that produces theta t, and by this I really mean there exists a sequence of function ft, and there exists a sequence of functions phi t from, say, rt to r, such that theta bar t is equal to phi t So in words, this is saying what? That any GFUM is equal to an AMP algorithm plus some post-processing. The important fact, of course, is that this function phi doesn't depend on x, right? So it's a deterministic function, it doesn't depend on the data. I will not go into explaining this lemma, but it's basically a recursive construction. You take basically the lowercase f that are the same as the uppercase f1, except for a change of coordinate, and then you choose the function phi to correct for the difference in the other function. Okay, it's not. Okay. Once you know that the lemma is true, then it's just a matter of matching the two iterations and choosing a function. And you prove that at each step you can find such a function phi. Okay, so the nice fact about this is that now I'm reduced to analyzing this AMP algorithm. Now, second point is that the analysis of A and P. And let me write a theorem now. I wrote this theorem in another form for regression, and but let me write it here because it's more explicit. And so fix any t, and then what you look is the empirical distribution of the true value and the iterates, okay. And the claim that this converges to the law of theta. Of course, the true vector converges to theta by assumption, and then a sequence of noisy version of theta. Where these random variables are defined like this: Z1, ZT, and let's say theta are, let's say mu, P theta, called P theta, the law of theta, times normal 0 times a certain covariance. This is a T by T covariance that I'll think as the first T by T submatrix of an infinite matrix. And now this coefficient, so now this law is completely defined once you give me the coefficient mu1, mu-t, and the matrix Q. And now I'll tell you how to compute this. You compute mu by the following recursion. And you compute Q by another recursion. This is okay. Let me write it like this. Perhaps it's easier to read. Okay. So we can precisely say what is the limit behavior of this algorithm in the limit n to infinity for any t fixed. Now, at the end, towards the end of the lecture, I want to, I'll describe where this theorem comes from, and for this, it's very crucial that you use the right term that is subtracted. But what is interesting here is that this fact that, in general, you wouldn't expect that the iterates of your algorithm are basically Gaussian modulo this theta term, but in this case, there is a Gaussian limit for this special algorithm. Okay, so let me, I want to describe two interpretations. One is that is very simple of this theorem, and another that is a little bit, less straightforward, but important. So the first interpretation is a relatively simple one. Okay, in these interpretations, I will think of theta, if you want, equal to 0 identically. And the first interpretation is related to the following simple fact. If V1 take two vectors v1 and v2 that are vectors independent of x, that in this case is equal to w because theta is 0. Then if I compute the two vectors z1 and z2 via zi equal x times vi, suppose that I compute zi in this way, and suppose that I have that the matrix converging to some q. So basically these are large vectors and their scalar product as a limit. Then what you obtain is that the empirical distribution of these two vectors z1 and z2, this is very simple exercises, just first class improbability exercise, converges, for instance, in W2 to a Gaussian with some okay. So if I take a single vector and I hit it with a GOE matrix, I get a Gaussian vector. I've got a vector with approximately Gaussian entries, and I take two vectors and I hit them with the same Gaussian matrix. You get jointly Gaussian vector. Now, in our case, what we are doing is that we are taking, I remind you the algorithm, we are taking a matrix and hitting a function of the previous thing, and then we are subtracting this term, this that we call the Onsager term or the reaction term. Now, you wouldn't think that this simple lemma or this simple remark applies to this setting because this and this are dependent. So this simple remark that I just made about the vector z's and v's seems to be completely irrelevant because x and ft are dependent because you computed θ1, θt using x. Okay, so they are completely dependent. There is no way that this simple lemma is going to apply. And in fact, in general, it will not apply. But because of this subtraction term, this Onsager term, because of this special term that I subtracted, because of the structure of the term that I subtracted, they act as if independent. So this is the magic somehow. So in conceptually, the theorem is saying that this update rule, the special AMP update rule, behaves as if x and f were independent things at each iteration for any constant number of iterations. So this is very interesting and still surprising. I have known this for many years now, and I found this still surprising. Okay, another interpretation now I want to give. Or perhaps I should stop here since we are halfway, and instead of rushing, see if there is any question.
Yeah, maybe I'll read this question to you.
Yeah.
So usually for rank 1 matrix problems like this one, we need to do an iterative method needs something like log n steps, but like yesterday, these resulted for fixed t. This seems like a disconnect. Is there some spectral initialization or similar?
Okay, so good point. Now, in reality, it depends. I can cook up examples in which you don't need log n steps, right? Suppose, for instance, that p theta, the prior distribution. So one standard example is be this distribution of the entries half delta plus 1 plus half delta minus 1. This is sometimes called Z2 sync. So you have a plus minus vector plus noise, and so in this case, you will need log n iterations. Now, suppose that I do something slightly different. I have 1/2 plus epsilon delta plus 1 plus 1/2 minus epsilon delta minus 1, right? So the vector has slightly more chance to be plus 1 than minus 1. Then in this case, I need only order 1 iterations, so a large constant number of iterations, simply by setting as initialization to my AMP algorithm. I can set anything that is as a positive bias, plus A. And so you can check that now the algorithm will converge in order 1 iterations. If you don't have such a unbiased, so if you really are interested in these problems in which there is no bias in the distribution of theta, this is indeed interesting. You can take as initialization V1 theta 0 that is V1 of the matrix X times a constant, okay? So now this kind of initialization for this specific problem has been analyzed, and basically things behave as you would imagine, right? So is again the state evolution recursion holds, provided that you initialize it with the correlation that is associated with this initialization, okay? And as I mentioned in the last lecture, it would be interesting to analyze, and probably it's possible, the AMP algorithm in a setting in which you don't use this initialization, you use random initialization, but you run log n iteration. But this so far, as far as I know, nobody has done it. But yeah, I think it's possible. Okay, so that was a good question. So perhaps I'll go ahead describing the second interpretation. The second interpretation is in terms of trees. So let me construct a tree Tn with vertex set Vn and edge set En. And this is the infinite tree of degree n. Okay? And I'll associate to the vertices. So this is an infinite tree of degree n. And associate to the vertices of this tree, IID random variables with distribution p theta. And to the edges, okay, to the edges, I'll draw IID random variable of normal 0, 1 over n. So I'm mimicking basically the same problem on a tree. And observation theta 0i, theta 0j divided by n plus wij. Okay, so let me draw a picture. So the picture is that, okay, it is for n equal 3. So this is not necessarily the case I'm interested in, because I'm interested in large n. But you have an infinite tree, and the theta 0i are associated to the vertices, and the xij are observation on the edges. And now I can state a perfectly honest statistical estimation problem that is given the xij, estimate all the xij, estimate theta 0. All right? So this is kind of the tree relative of my statistical estimation problem, low rank estimation problem. And now, here is an algorithm, a class of algorithms for this. So what I'll do is that describe a connection between the original problem and this problem. And for doing this, let me introduce a class of algorithm for this problem that I'll call message passing. These are algorithms in which you operate with messages, ui to j. There is two of these messages on each edge of this graph. Okay, so let me perhaps draw it here. So on each edge of these three, I have two messages going in the two directions. And to indicate directions, I write xij. And these are updated in the following way. This is the sum of in the neighborhood of I minus vertex j. And then I apply ft. So this is the same ft of my AMP algorithm. Okay, so I define this class of updates. Now, the nice fact about it is that this is a relatively simple class of algorithm to analyze, and to explain why, let me define a sigma algebra, Fij. So this is the sigma algebra generated by all the randomness okay, that is in the tree Tij, and I'll describe in a minute what this tree is. Okay, so what is the tree Tij? I drew before this tree. So let's say that n is equal to 3. So this is a ternary tree, infinite. And the tree Tij is this tree here. Okay, so the tree that includes all, includes all the vertices that can be reached from J through a path that first visits I and doesn't come back to I evermore. So here is the tree on the left, the subtree on the left. And now the remark is that one important remark, let me write one, is that ut I to j is in the sigma algebra Fij by construction. So it's, I use only information, at each time. When I update this message, I use information coming from these two messages. This is the way I did it. If you look at the update, when I update I to j, I use only information from vertices L that are on this side. Okay, from this reason, this only, it's measurable with respect to that. And in fact, with respect to less than that, only, if I call these only those that have up to distance t from vertex I, is even measurable with respect to that. Okay? Because of this, it turns out, as a consequence of this, it turns out that you can analyze quite precisely, quite easily, this algorithm, because basically when I compute ui to j, the message here on this edge, I'm computing an operation on two messages L to I that are independent. In other words, if you look at this iteration, at each iteration, all the summands here, all the terms here are independent. okay? Because the corresponding trees are disjoint. So this is a sum of independent terms. And because of that, you would expect that for large n, this guy is Gaussian by central limit theorem. The messages incoming are independent because they depend on distinct sum trees. And therefore, you know, perhaps I can apply the central limit theorem to compute this sum. And therefore, this guy will be approximately Gaussian. And so this is indeed true. That is, observe the, you know, you can prove an evolution thing for this algorithm on tree. So if I look at these messages for t iterations, this has converges in distribution to, okay, so I should write, and then so because of you are summing independent contributions, many of them you can apply CLT, and turns out that you get a, you know, a limit theorem for the distribution of these messages. Now I called these guys, this limit variable on the right hand side, in the same way as I called it from my AMP algorithm. And this is not because I want to create confusion, because those are the same random variables. If you choose the same function f, you'll get the same limit for you. Sorry. Now I apologies. I've been calling this u on the tree too. I've been calling these guys u's. Sorry. So I hope this didn't create confusion, but you know, the basic reason is what I said before, right? The interpretation of the state evolution is that X as independent of the, you know, of F, and here is the same. Yeah, here really, okay, the way I define T actually shouldn't include that edge. Tij actually should be defined this way. They shouldn't include this edge. Okay, so now what is the situation? We have an algorithm to do this rank 1 estimation problem on a finite n, and you know, on where n is the, you know, number of variables, and we have an algorithm to do this rank 1 estimation problem of an infinite tree. Now, these are two different problems. One is an infinite tree with degree n, and the other is a finite graph. And basically, the two algorithms, we proved that they behave the same way. So if we want to prove a lower bound for the algorithm on, you know, the original problem, it's sufficient to prove a lower bound for the problem on the tree. Okay, so now this is the third part of the proof, is where you will finally prove the optimality of Bayes AMP among all AMP algorithms. And the idea is what I just said, is that you know, it's sufficient to prove lower bound on estimation, okay, or for estimation. By the way, these problems of doing a statistical estimation of infinite trees it's an interesting area in itself. I think that is a little bit, yeah, you know, Okay, it has been explored in some cases like community detection, but for instance, you can construct a problem on a tree that is associated to linear regression or to phase retrieval, etc. Now you want to prove a lower bound for estimation on Tn for all message passing algorithm. Now, what we'll use to prove a lower bound, okay, I will not do really a proof, but what one can use is the fact that message passing is a local algorithm. What does this mean? It means that your messages I to j are measurable on the sigma algebra generated by all the XLM with LM in a ball of radius t around I. Can be t plus 1 or t, doesn't really matter. Okay, so at each iteration I aggregate information from one more step, one more distance. So after t iteration I only aggregated information within a finite ball. Therefore I'm not doing estimation on this infinite tree in an arbitrary way, and actually I don't necessarily even know what that means. But I'm doing estimation at each vertex in a local way. Okay, now there exists an optimal local algorithm so, message passing algorithm a special subset of local algorithms, but there exists an optimal local algorithm. And this is simply what? It simply estimates at each vertex I by computing the posterior expectation of vertex I given all the guys right? So there exists such a local algorithm, right? You just compute the posterior expectation with respect to everything that is in the final ball. Okay, so this is a lower bound, and turns out that this can be implemented at least for large n as a message passing algorithm in the sense that I described before. Okay, so because of that, that's not only a lower bound, but first is a lower bound that you can analyze, for which you can write explicit recursion, and in fact is tight because it can be implemented as a message passing algorithm in the tree, and therefore can be implemented as a message passing algorithm on the graph. Okay, so I will not describe, so all the steps before kind of described at least at high level the reason. I will not describe the reason for this last point, but the reason is related to writing a belief propagation algorithm. And actually, Michael will in his session, in his lecture, he will explain this connection. Okay, so that's somehow at high level the proof of optimality, this thing, and of course there are all sorts of interesting questions that one can try explore here, but this is what we know so far. Okay, so in the last 10 minutes, there is one kind of mystery that I didn't explain, is why So I stated a theorem about state evolution, and I didn't explain why. I gave two intuition, but I didn't explain any reason why we should expect. So why should we? Anything as state evolution. To hold. Okay. And here for explaining that, I'll use the case theta 0 equals 0. I'll use the same problem, but I'll take the case in which you don't have any signal, because okay, let's simplify a little bit the argument. And so therefore, what we are interested in is really this iteration. W is a GOE matrix. And then I subtract this carefully chosen. Term. Okay, so what is the argument? So there are a few different arguments. I'll describe one that I think it's simple. I mean, it's simple. It shows quite easily that there should be something like this working. And the idea is the following. Let me define GT to be the sigma algebra generated by theta 1, theta t. Okay. Notice that I can write this equation. Let me define xt plus 1 as theta t plus 1 plus whatever is on this side, whatever is there. So that is plus sum over s1 to t d ts fs minus 1 theta 1 theta s minus 1. So this x is a vector. And this set of equations, this equation here, in terms of this vector, you can write it as xt plus 1 equal w, and let me call ft the vector that you apply by, let me call this the vector ft. And now I want to think of conditioning on the sigma algebra GT. And the claim is that this is equivalent to condition on the value of these linear equations. That is on x1 equal wf0, x2 equal wf1, blah, 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 xt equal w ft minus 1, right? So if you give me all the vectors up to time t, it means that I know that all these equations hold, right? So what do I have? So I can write this in matrix format as xt equal w ft, where for instance xt is the matrix that has column x1 to xt, and ft is the other matrix. Okay, so this is really conditioning a Gaussian matrix on the value. So the Gaussian matrix is W. So condition a Gaussian object on the value of a linear operator, a linear function of this Gaussian object, because W times F is a linear function of W. And you know that if you take a Gaussian and you condition it on the value of a linear function of this Gaussian, this is distributed as the conditional expectation plus the projection of an independent Gaussian on the kernel of that linear operator. Okay, so in this case, this general fact is the same. You can write it as follows. Condition on GT, W is distributed as the projection orthogonal to the columns of the matrix FT of a new matrix plus some conditional expectation. The conditional expectation of W given GT. And this conditional expectation is really some function that I'll call it M, some matrix that is some function of course, FT. So, XT and FT. Because that is all I know on GT. Okay, so this is so this is a special special example of the general fact that if you take a Gaussian vector and you condition of being on an affine space is equal to the conditional expectation plus the projection on the kernel of an independent Gaussian. Therefore, if I look at theta t plus 1, I can write it as P. You remember the equation here. The update equation was this. So now let me replace W by the new expression for W, and I'll write and then this is F T. This is really F of the previous thing. And then there is plus this matrix M of XTFT applied to F T minus 1 minus sum over S to T of DTS Fs minus 1. So this is just an identity. This is true in distribution if you want. It's just an identity. But now this, it's quite clear the way to go, right? This is, I think it's quite elegant. I can say it because it's not my, first of all, here what you have, this vector is this vector that shows up here is a Gaussian vector because W is independent, W nu is independent from the past. So the little lemma that I stated before, or the little remark, you take a fixed vector, you hit it with a GOE matrix, you get a Gaussian vector. That lemma applies here, okay? So this whole vector is approximately Gaussian and is a vector in n dimension. Now I'm projecting a high dimensional vector orthogonal. This FT, this projector is the projector orthogonal to the column space of F. So it's a projection on a space of rank n minus t. Okay, so this is of rank n minus t. So I'm taking a vector that is Gaussian in n dimension and I'm projecting out T of them. T is of order 1, n is very large. This will not make any change. Okay, so I can drop this projector and I will make a negligible change, a negligible error in L2 sense. And then you get this whole thing, okay? And you can make, since this is a function of x and f, so this is a function of x and f, you can figure out that this, you can write it as a sum of certain coefficients times, whatever theta t, and then some other coefficient d prime. Okay, so you can express it in this form, and then you subtracted. Okay. F. Okay, so this piece we like because, you know, by induction you prove that theta is Gaussian, a previous iteration, and so these two pieces together make a Gaussian vector, because this, the first one is Gaussian. We said is a matrix, a Gaussian matrix applied to a fixed vector, to an independent vector, and this is Gaussian because by induction up to time t, this should be S. By induction, so this is for S less than t. By induction, the previous iteration were good. The pieces that you don't like are this one, but you see that you can choose the coefficient d as to cancel these ones. Okay. Now all the thing that you're left to prove basically is that, okay, all of these coefficients here, I wrote them. You know, I said, okay, this is Gaussian, and therefore, so I am assuming implicitly that these C concentrate, they are deterministic, and so this is something that you have to prove, and you have to prove that these two, you know, the expression, the special expression for D that I wrote before cancel with the special expression that I, you know, with whatever you get from this calculation. So that is a calculation that you can do, and okay, I will not explain that, but this is the basic idea why, you know, you get this Gaussian thing, that you choose exactly these coefficients as to cancel this non-Gaussian part from the past. Okay, that's all, I guess. And okay, so tomorrow I'll apply basically the same thing to describe how to get you know, approximate ground state of Ising spin glass models.
Okay, well, I'm going to unmute the participants so we can thank Andrea.